In this video, we're going to be calculating ionic strength. Now remember, what is ionic strength? So your ionic strength of your solution is whenever you're saying how much is the salt that may be present in your sample, how much is it affecting the activity of your analyte? Because your analyte is just not all by itself acting independently. It's surrounded by things. It's in a solution. And so because of that, it can have an ionic radius. It has water that's around it. It has salts that are around it. And those salts are going to affect the activity coefficients, the activity, all of the different activity equations that you're going to have. It's going to be affected by the salts. So before you go and do any of these activity problems, basically just equilibrium problems that incorporate activities, you need to calculate the ionic strength of your solution. So how do we do that? We're going to learn in this video. So here's the equation for ionic strength, where your ionic strength, your mu, is equal to 1/2 of, here, your concentration is your C and your Z is your charge. And that's for every single chemical species in your solution, all of your ionic compounds that are affecting your activities. And so C is your concentration, Z is your charge. So if it has a +2 charge, that's a 2. If it's -3, or whatever, then it's going to be a -3 here in the middle. But it's squared so that plus or minus doesn't affect it at all. All right, so let's do this. Let's practice. If we throw sodium chloride into our solution, we'll end up with sodium chloride going to sodium and chlorine. And so that tells us the charge of each of our species. And so now we just come and bring it over here into this equation, where our ionic strength equals 1/2 times the concentration of our sodium. If it's 1:1, if you start out with 0.1 molar of sodium chloride, it's going to break and you're going to have 0.1 molar of sodium and 0.1 molar of chlorine. And so because it's 1:1, that's how much you're producing. So my concentration of my sodium is 0.10 molar times its charge squared, plus my concentration of my chlorine, 0.1 molar, times my charge of my chlorine, -1 squared, brackets. If I had more ions, I would just keep going. So here, my final ionic strength equals 0.1 molar whenever you put that into your calculator. Let's do another one. Here we have 0.10 molar, so same thing. So you may think, oh, it's going to be the exact same. But it's not, because here it's sodium sulfide. Sulfide has a 2 negative charge, and so that's going to change your concentrations and also your charges that are placed into your ionic strength equation. So sodium sulfide, it reacts and it releases sodium ions and sulfide ions, but it releases 2 sodiums for every one compound. And so if that's the case now, how much sodium is going to be produced? If you start out with 0.1 here, you're going to produce 0.2 sodiums. And you're going to produce 0.1 is going to produce 0.1 sulfurs. And so the ionic strength, the concentration of each individual species is going to be different depending on which one you're looking at. And so just once again, make sure you can think through that in your mind. If you start out with 0.1, you're producing twice as much for every single ionic compound that's placed into your solution. So here, my ionic strength equals 1/2 times my concentration of my sodium, which is 2 times what it was initially, so 0.2 times my charge plus 1 squared, plus my concentration of my sulfur, 0.1 times my charge of my sulfur squared. Now when we place all that into our calculator, we end up with 0.30 molar, which is very different than if it's sodium chloride. So what you should notice here is that the more doubly, the more triply charged your species is, the more charge on your chemical species, your ions, the greater change it's going to have on the ionic strength of the solution, which makes sense, right? All right, because the more charge it has, the more, kind of think about it as magnetism almost, the more it's going to affect the solution. All right, so we've done 2 examples. This one, when we do this one, students are like, well, what happens here? We've got 2 species. Let's include all of it in our ionic strength equation. Okay, so we got to turn magnesium sulfate, turn that into its individual ions, and then same for calcium chloride. So magnesium sulfate turns into Mg2+, and SO4 2-, whereas calcium chloride turns into calcium 2+ and chlorine minus. But how many chlorines are there? 2. All right, and so we need to make that change. Make sure we note that my concentration of magnesium is 0.1, concentration of sulfate is 0.1, concentration of calcium is 0.2, but chlorine, what's my concentration of chlorine ions? It is twice what it was originally, so it's 0.4. And so when we put all of that into our ionic strength equation, you need to make sure you take that into account. So let's calculate that now. Ionic strength is 1/2 times my concentration of my magnesium times my charge, 2, squared, plus concentration of my sulfate times charge squared. Remember, it doesn't really matter if you put the plus or the minus there because it's going to get squared, so the charge is irrelevant. The charge is not irrelevant. Whether it's a positive or a negative is irrelevant. Plus my calcium concentration, which is 0.2, times my charge on my calcium, squared, plus my concentration of my chlorine. So remember, that's 0.4, because it's double my 0.2. And then my charge on my chlorine is 1, and that is squared. If you put all of that into your calculator, you're going to end up with the final ionic strength equal to 1.0 molar. So a lot larger than the individual entities, but that's because you've got double 2 charges on, +2, -2, and then another +2 on your species. And so when you calculate ionic strength, remember you're doing all of this work just so you can take this ionic strength and place it in a table or use the Dibby-Huckel equation in order to calculate those activity coefficients. And so in a future video, we're going to practice doing that.